Welcome to today's video where we're going to look at our second and third types of transformations that can be applied to functions. We're going to look at what are known as reflections, and we'll follow that up with an examination of how you stretch a graph. All right, so we're going to start with just a quick overview of what exactly do I mean by a reflection. Well, a reflection is when you get a mirror image of a graph. So you can take, for example, a graph like this that opens up and apply a reflection to it, which will turn your graph over and make it go this way. Now, we'll just talk about that one first. So, or vice versa. It could be a situation where a graph maybe opens to the left, you reflect it, and it'll open to the right. So you can have a line of reflection that will either be the x-axis or a line of reflection that will be the y-axis. It will depend upon where we put our negative value that we're going to use to reflect a graph. Looking at our first situation, if we took some function y equals f of x, let's use this graph here and say, well, this is my function, y equals f of x. There you have it. And then I took the function f of x and I multiply it by -1, so that my new function is y equals negative f of x. First function, this one, I get all the y values by just taking my, whatever this function is, I fill x in and I get my function value. Well, this one says do the same thing except take the negative of all your answers. Well, essentially that's going to turn all the y values I got here, they're going to become the negative of what they were, because we're taking, here I had just of f of x, here I have the negative of f of x, which is telling me to take the negative of all my y values. Imagine you had this graph, let's say this point, which is situated at 2, 3. Well, if you take the negative of that y value, don't change the x, leave it the way it is, but you took the negative of your y value, that would make it become -3. So this point would switch down here and go from 2, 3 to 2, -3. Right, this point right here is still x is 2, but now the y value is -3. If you had this point, I don't know, here, let's say this one's 4, 7, right, that point, well, it's now down here at 4, -7. This point here is now down here. So all these points, that's what they mean by a reflection. You have all your points reflect across or in the x-axis. So we say it's a reflection in the x-axis. So if someone says, how do you reflect a graph across or in the x-axis? You multiply your function by a negative. All right, so y equals negative f of x with the negative out in front of your function is what we call a reflection in the x-axis. The second type of reflection would be the one we see situated here. And this is where, rather than multiplying the output, what you get after you apply your function, you're going to multiply the input, meaning what you put into the function. So instead of filling in, let's say this was a 2, now we're going to fill in a -2. And when you do that to a graph, what happens is all your x's switch values. For example, let's suppose the green one was our starting one. So I've got, let's pick a point that I can see here. It's not a great graph. Let's say this one, right here. At -1, I'm hitting the graph right here. I don't know, somewhere around, there's scales 5s, somewhere around 4. Well, all that's going to do is going to go straight across and hit the graph there. This point, which was -1, let's suppose it was 4. Well, now that's situated at 1, 4. Imagine you did that for every single point on this graph. So let's say you had this one, which is at 2, it's not quite 2. So 2 hits the graph right about here, so 219, let's say. Well, then it should be at -219, which would be right here. and it did line up with that one. So this point went to here, this point went to here, this point went all the way over to here, this point went all the way over here. So they're getting reflected. All these points are going here, all these points are coming back this way. The only one that didn't move was this one right here. Well, the reason it didn't move is because it was the ordered pair 0, let's say it was 7. Well, if you multiply the input, the x, by a negative, it's still going to be 0. It's not going to change. So that one stayed the same. We'll talk about that in a moment. It's called, we have a special name for it. This is the situation where the graph got reflected in the x-axis, in the y-axis, across this vertical line. So when your graph goes side to side, think about that as in your x's are switching from negatives to positives or positives to negatives. When that change is happening, the line of reflection is the vertical line called the y-axis. So if y equals f at negative x, you get a reflection in the y-axis. All right, so let's look at a couple scenarios. Oh, this is how, so I was just mentioning that when you apply a transformation, like the one I just did a moment ago, I had a point that didn't change. That point has a special name, and it's called an invariant point. So by definition, an invariant point is a point on a graph that doesn't change when you apply a transformation. It stays exactly where it was. If I just backtrack for a second, this point right here was the only one. It was invariant. Now the only way that you get invariant points is if they are points that are on one of your lines of reflection. So for example, on the y-axis, if you're reflecting it across the y-axis, that one stayed the way it was. Now if I go to the other graph and I said to you, do you have any invariant points here? The answer would be no, because every single point that was here ended up somewhere down here. They all moved. Now let's suppose my starting graph had been this, something like that. Let's suppose it touched right here. Draw that very well. It's hard with this pen. And it opened, there's the reflection of it. Well, you'd have this one point right here that didn't move because it was on the line of reflection, and it would have been called invariant. All right, so that's a new term that I suspect most of you have never heard tell of before, but it is a term that I would expect now moving forward. If you hear it, you know what I'm talking about. So here's an example of a picture, a graph. This is some graph of f of x. It says sketch negative f of x on the same axis. Well, negative f of x means make the outputs. So this is telling me to make the outputs, which is graph talk for y values. Sorry, not make them. Let's multiply, be a better word than make. So multiply every single y value on the graph by a -1. Now we're not going to literally do every single point. We're going to pick these key ones that kind of will move the whole graph for us. So this one here is at a y value of -3. Multiply that by a -1, it's going to now be at y is 3. This one's also at -3. It's going to 3. This one's at 0, not going to move. What's that name again? Invariant. That's an invariant point. 4 will end up at -4, and -4 will end up at +4. Here's the new graph. Straight across to here, down to here, and up. Oof, that should be a straight line, but it's a little hard to do with this stylus that I got here. Try and draw that again. There, to there, to there. It's a little better. Okay, so you can, if you look at these two graphs, the red one is reflected, or is a reflection in the x-axis. All the points went across the x-axis. So we say it's reflected in the x-axis. And the way that happened was by putting a negative out in front of your function notation. Just have my answer down below here. There's the computer-generated version, so ours wasn't bad. All right, let's look at the situation where now we multiply the inputs by a negative x. So when you see this notation, it's implying that you should multiply every x value by a negative 1. X is negative 4, x is negative 4, x would now become positive 4. X is negative 2, x would now be positive 2. X is 0, x is still 0. X is a negative 1, multiply that by a negative, it'll switch, sorry, x is positive 1, it'll become negative 1. X is 3, it would become negative 3. X is 5, x would be negative 5. Now, let's try and draw this. Up, down, it keeps going through there, and across. So these two graphs got folded or reflected. That one went that way, this came here, this went over this way, but everything was going across the y-axis. We say that graph got reflected in the y-axis. And in order for that to happen, you need to multiply all your x values by a negative 1, which will happen by inputting a negative x into your function. All right, so those are reflections. Now we'll look at stretches. Now a stretch is where you change the distance of every x coordinate or the y coordinate from the line of reflection. So you either stretch them vertically, so imagine you had a graph and you pulled it up this way, well, that should change the y values, versus a graph that you take and let's say you pull it out this way and stretch it wider, that will affect the x values. So that this one's called a horizontal stretch, this one's called a vertical stretch. So kind of just get that connection that a vertical stretch will have an impact on the y values versus a horizontal stretch that's going to have an impact on the x values. We'll talk about scale factors and whether the scale factor will determine whether the x values are going to get further away or closer to the line of reflection. And we'll focus more on that when we get into the details here to follow. All right, so the first thing is stretches. Unlike any of the other transformations, your translations and your reflections, it's actually going to change the shape of the graph. The other two, they don't change the shape of the graph, they just either change the orientation, meaning whether it goes up, down, or left, right, or it changes the location of it, moving it left, right, up, down, whichever. Okay, so how do we make this happen to graphs? Well, this is going to happen if you take, for example, the first situation is you have your function, y equals f of x, so f of x would be your outputs, and you decide to multiply them by a constant. So imagine that you got your y values, but then instead of y equals whatever, you're going to put a 2 in front of there. Well, if you put a 2 out in front of your f of x values, so put a 2 here, that's going to make all your y values be twice as big as they used to be. Think about how that would impact a graph. So if you had a graph and you doubled every y coordinate on the graph, well, that would pull it up in the air, because now if you had a number that was originally at a 1, well, now it's going to be at a 2. If the y value used to be at 6, now it's going to be at 12. Every y value would get doubled, which would stretch your graph straight up in the air. If you wanted to compress your graph or squish it down, you would want to, instead of putting a 2 there, maybe put a half there. Think about that. If you had all your y values and you took half of them, instead of your graph going up to 4, now it only goes up to 2. Instead of going up to 6, now it only goes down to 3. So that would have the visual effect of compressing your graph down and making it have a vertical stretch in such a way that your y values are now smaller than they used to be. Now they use this notation, absolute value. Absolute value just means ignore, if there's a negative on it, ignore the negative. The negative has a control over the reflection, but it has nothing to do with your stretch. Your stretch is just looking at the number in front. So again, it just means if there was a negative a half here, the absolute value of negative a half is just 1/2. So your stretch factor is never negative. It's always the absolute value. It would be a half. The other type of stretch is when so rather than putting it out here, you substitute it in here as part of your input. Now by putting f of bx, so that means instead of substituting x's, fill in 2x's or 3x's or 4x's. Now this one you have to be careful. The effect of this on a graph is if you put f at 2x, the stretch factor is actually going to be 1/2. Our brains might think, oh, we're going to double the x's. When you input 2x into a function, the actual impact on the graph is it makes the x values half of what they used to be. If you input a 5 here, the x values would be 1/5 what they used to be. If you had a graph that looked like whatever, and you make the x values get smaller, well, that's going to compress your graph together because it's going to move the x that was here over here. It's going to move this x here, here, and it's going to make your graph get narrower. Versus they say, well, how do I make the x's move further away? To make the x's spread further apart, you need to put a fraction here. For example, if you put 1/4 here, well, if b is a fraction and you put 1 over the b value, which is already a fraction, well, 1 over 1/4 is the same as 1 times 4 over 1. That would make the y value, or the x value, sorry, be 4 times what they used to be. In the beginning, this can look and sound a bit confusing. It's really not. There's just a few facts we got to study in terms of when we put numbers in, what will the effect be. So I'll show you a couple more examples. Here's a visual example of a vertical stretch and see if you can get your head wrapped around it. Here's 3 functions. Y equals absolute value of x. So my function in this example is f of x is the absolute value of x. It is the red broken line right here. That's our base function, f of x. Well, this example is y equals 3 multiplied by whatever the original f of x was. That one means all the y values are going to be, they're not going to increase by 3, they're going to increase by a factor of 3, meaning multiply the y's by 3. Okay, by that number. Let's look at how that played out on the graph. So look at the red one. So the red one was at 1, 1. The y value is going to get multiplied by 3. We're not going to touch the x value. So it's still going to have an x value of 1, but instead of 1, 1, now it jumped up to 1, 3. Look at 2. 2 used to be at 2, 2. So the x value was 2, and the y value was also 2. By putting a 3 out here, it will triple the y value. Instead of 2, 2, it should now be 2, 6. Right, so 2, 6. This one became 1, 3. So the x stayed the same, but the y value got tripled. X stayed the same, but the y value got tripled. So what that did, if you look, this was originally 1 unit up, now it's 3 units up. This was originally 2 units up, well, now it's 3 times that. It's 6 units up. So if you get way out, now we're not going to be able to graph it, but let's say it was way out here at 6. So this was 6, 6. Well, the new point, when you stretched it, so if that green graph kept going up off the page there, it should be at 6, 18 when you stretch it up there. If the stretch factor was a 3, you would triple the y value. Versus this one. This one, with a half out in front of it, I should take half of every y value. Well, when I take half of the y values, let me get rid of this red stuff so I can see it better here. All right, let's examine what happened visually here. Well, we'll go back to our 1, comma 1. So it was originally at 1. So the purple one is this graph here. So it's in purple. Now it's saying take half the y value. So instead of being at 1, comma 1, it's now at 1, comma half. This one was at 2, comma 2. Now it's at 2, comma 1. We had 4, which was at 4, comma 4. Half of your y value will put you down at 4, comma 2. So that one, maybe you can see, or hopefully you can understand, that they will sometimes call that, rather than a stretch, they'll call it a compression. It's almost like you took the original graph and you, and you squished it down that way. Notice this point didn't change in any of the transformations. And the reason it didn't change is because it was the ordered pair 0, 0. If you have a y value of 0 and you multiply it by 2, 5, 10, a half, -2, it'll never change. That's why it didn't move. That's why it's, in this situation, would be another example of an invariant point. It wouldn't move. Now let's examine horizontal. We'll do the horizontal and then we'll come back to that. Here's the visual of a horizontal just to show you. So this time my function in red, so f of x, the base function, is the absolute value of x. So now this one would be an example of f at 3x. So I've put 3x in where the x used to be. Now I want you to look at the impact of the graph. So I just did this on a piece of graphing software, Desmos, and here's what it came out to look like. Well, if I pick some points here, let's take one that I can work with. Well, this one here, for example. It was the ordered pair 1, comma 1. Now look at this graph, the new one. Now it's this point, which we'd have to estimate, but it is the ordered pair 1/3, comma 1. So the y value stayed the same, but the x value became 1/3 of what it used to be. This is one that'll be easier to see right here. This was the ordered pair 3, comma 3. Well, according to this, if I look at the new graph, now I'm sitting at 1, comma 3. So I think you'd agree that I divided this by 3, or I took 1/3 of the x value. Another one we could see, let's say this one, 6, comma 6. Well, if our thinking is right, on the new graph, the green one here, I should be dividing this by 3, so I should be at 2, comma 6. It's exactly where it ended up. Look at that, 2, comma 6. So what happened was I multiplied every x by not 3, I took 1/3 of them. This one is the reciprocal. So in a horizontal stretch, excuse me, it's really important that you realize when you do horizontal stretches, you take the reciprocal of the number that's been input in the function, and that will give you what you're going to multiply. That's your stretch factor that you'll multiply all your x's by. So look at this one. I had f of x, I put a 1/2 in there. So if my logic is right from the last question, the reciprocal of a half, I should be multiplying every x by 2. Let's look at this one. For example, this was the ordered pair 3, comma 3. Well, putting a half there, this is the new graph. Let's see where it ended up. 6, comma 3. So is our logic making sense? Multiply every x by 2. X was 3, now it's 6. Makes perfect sense. Let's look at this one. Right here. Oh, I missed it. I guess they did this one, 5. So this was 5, comma 5. The new graph should have a point then 10, comma 5. Let's see where I hit this graph. Look at that, 10, comma 5. So our thinking is correct. By putting a fraction in here, it doubled all the x's. The y's did not change. Now, if I just backtrack for a second, I missed that one. If I wanted to draw on these graphs, so let's do on the first one, let's sketch twice f of x. So these are when the number's out in front of your output, it means you're going to double the y values. This one's at 4, which means the y value should now be at, now the x won't change, but the y value will go to 8. 8 is right there. The y value here is 0. It's not going anywhere. It's going to stay at 0 because 0 times anything is 0. The y value is 2. It's going to 4. 0, stay where it is. 4, y value is 4. Double the y value. It's 8. Here's my new graph. So this would come down here. That stayed. That went up to there. This one stayed. And that went up to there. All right, let's do a half of f of x. This one says take half of every y value. This one would drop to here. This one wouldn't move because the y value is 0. Take half of 2, you'd be here. Half of 0, still 0. Half of 4, 2. Here's my new graph. Line. Those are examples of vertical stretches. The top one would be called a stretch. This one is often still called a stretch, but you may hear it sometimes called a compression. Think of compression like squeezing together. It's like taking the blue graph and squishing it together versus the other one where you're taking the original graph and pulling it up in the air further. That's called a vertical stretch. Anyway, stretch is fine for both of them. Let's look at horizontal. Oh, I don't have my graph. Let's try and do it for one of those if we can. Let's go back, steal that graph. Let's just take the graph only, copy it, and let's do a horizontal stretch on that. So let me look at, yeah, let's do this. So let's look at the graph of f at twice x. So this implies for me to take half of every x value. So every x, take half of it. Okay, so the x value here is -6. It will end up at -3. Y value won't change. X value is -2. It'll end up at -1. X value is 0. It won't move then because that's 0, 2, so it would stay where it is. X value is 2, it'll go to 1. X value is 6, half of it would take it into 3. Here's your new graph. So you see how it took the W and squished it together? We would call that a horizontal compression. If you said, how would I make that get wider then? How would I stretch it out further? I'm not going to draw it on the same one because I don't think my scale will accommodate it. But if I did this, this would imply that I should double every x value. All right, so those are your reflections and your stretches. Now let's kind of put those in play and see what kind of, this is just a summary of all the transformations from start to finish. So we started out by, if you take a function, you add a number at the end, that's called a horizontal translation of up c units. Another vertical translation, up down is vertical. Subtract c, shifts it vertically down c units. Input a plus c, shifts your graph left c units. Input a subtract c will shift your graph right to the whatever c units would be. Input a -x, reflects it across the y-axis side to side. A negative in front of your function will reflect it top to bottom, so that'll switch your y's from positives to negatives, so that'll be in the x-axis. A number out in front of a function will be a horizontal stretch. Now they just say that if it's between 0 and 1 means it's a fraction. That's going to make the y values be smaller. You're going to multiply them by a fraction, so it'll compress it together. If you multiply it by a number that's more than 1, it will make the y values bigger, which will stretch it and make it the numbers higher. If you input some constant into the function, that's called a horizontal stretch. And if you input a c, so if you input a fraction, it's going to mean you're going to double or triple or quadruple, whatever that fraction is. So like a half, you double it. 1/5, you'd multiply them by 5. But if you put a number that's more than 1 in there, you're actually going to multiply the x values by a fraction, which will make them smaller and have the effect of compressing it together, or a horizontal shrinking. All right, so that's a chart that summarizes all of the transformations. So that's kind of if there's one, out of all the explanations and everything I showed you, this is what you really need to know. C in all of these is just a constant, any constant. Applying a mapping rule. We talked about mappings in translations. So if we put that all together now with reflections and stretches, and we think about this, the number here in front, this has an impact on the y values. It will make the y values be that number multiplied by all your y values. Therefore, whatever's here, you would want to multiply your y values by that. If it's reflected, this would just be a negative. Well, then you'd multiply by a negative and the number. So that would do, a negative would reflect it, the a would stretch it. This is your horizontal stretch. Same thing, it could be your horizontal, or it could be your reflection as well. If it was a negative b, this is the one that's reciprocal. So it would be 1 over b. If it was a negative, it'd be negative 1 over b. That would reflect it for you of all your x values. A negative c or subtract c, you add c to all the x values because you're going to move it right. If it's a plus d, you would move your graph up d units. So this is kind of a generic version of transformations as a mapping rule. It's going to be really important that you're able to write these and understand how they work. We'll do some of that here in a moment. This is important. It's an acronym. This is called an acronym, RST. Reflections, stretches, translations. Those are always the order you examine functions for transformations. Always do reflections first, then your stretches, and translations comes last. Okay, so let's put this into play and see how this all works. The one thing I will tell students at this point is that this is a section in the course that, and I mentioned this in class, I believe, there's facts about transformation you need to study and know. For example, knowing there's a 3 here, I'm not going to do any work. I just need to know from studying or from me showing you those examples that this is going to triple all the y values. It's going to make the y values be 3 times what they used to be. So this is saying if you had the point negative 2, 5, and you put a 3 in front of the function, well, if I look at how mapping works, this is how a mapping works. X, Y, if I wrote a mapping for this, putting a 3 there will have no impact on the x's, but it will triple the y values. Well, the way this works then is you take the point from your base graph, negative 2, 5, and now you apply this rule to show you where it would end up on the new graph. So x isn't going to change, but you're going to triple the y value. Now, do you have to write a mapping for these? No. If you can keep track of it all in your head, and when there's only one like this, you probably can. But when you get down to these ones that have multiple transformations, I would definitely be writing a mapping to help me figure out my new coordinates. So this one, f at negative 1/3 of x. If I was doing a mapping, it would look like the following. So a negative is going to reflect your x's. So you're going to multiply all the x's by a negative, and a 1/3 is going to triple them. So negative 3 times all the x values, no impact on the y. The only thing that changes the y values are numbers out here and out here at the end. Anything input in the function will have an impact on the x's. All right, so negative 2 and 5, apply the mapping rule, negative 3. So all you do is you fill x in as that number. So if x was negative 2, you'd get a 6. Y is just going back in as your y value. All right, let's put some more transformations into play. So this one, my mapping, would be, so let's start with the x's. Remember, the x stuff is inside the function. You're going to double the x's, and then you're going to move it left 5. So left 5 would be that. You're going to multiply the y's by 4, and then you're going to move them all down 3. So if I did all of that to the ordered pair negative 2, 5, and I'd like to know where would it now be after doing all of this to it, it would be at 2 times negative 2 is negative 4. Take away 5, so negative 9. Fill 5 in for y. 4 times 5 is 20. Take away 3. That's where it would now be situated. This one has one little extra step. We want when we identify all of our transformations, we want to isolate the y equals or g of x equals or whatever that other variable is. So I'm going to get the y isolated. So it would be negative 2f. The other thing is when you identify your translation, you need to have a 1 inside this bracket. You'll notice here I have negative 2x. So some students will look at this and say, oh, it goes left 6. No, it doesn't go left 6, and I'll show you why. When you're writing this out, you need to factor off any coefficients. This one was already factored for you because you may say, well, I didn't do that here. You didn't have to. It was already done for you. See, the brackets were there. I have to do that with this one. So I'm going to put a negative 2 here. Divide this by negative 2, you get your x. Divide plus 6 by negative 2, you're going to get a minus 3. Negative 5 moved over will become a plus 5. Here's our mapping, x, y. So here's the x information. I'm going to take and multiply every x value by a negative and then the reciprocal of 2. So negative a half. There's my reflection and stretch. I'm going to go right 3 plus 3. I'm going to reflect every y value and double them. So negative 2y, that'll reflect and double the y values. I'm going to move them up 5. I'm now going to apply those transformations to the ordered pair negative 2, 5 and see where its new home is. Negative a half times negative 2 is in positive 1 plus 3. We're at 4. The 5 will be at negative 10 plus 5. It would now be situated there. So that's how mappings tie in with transformations and how they work. Okay, these can be a challenge. In this one, we're given a function. Now we got to read the instructions, and we're going to try and build a new function and write a correct function notation that would turn. So what does it want me to do? So the graph of y equals g of x is a transformation of y equals f of x. G of x is a transformation of f of x. So this was the starting graph. And I want to figure out what did I do to this to turn it into this new graph. Well, let's look and see what happened here. Remember the order? R, S, T. Always look for them in that order. Let's start with reflections. Do you think that this graph got reflected across the x-axis? So did this point flop down to here? I would say based on the way this is drawn, it was reflected in the x-axis. Now it didn't get reflected in the y-axis because if it did, even if you had to say, well, it did both, it would have went down here, but then it would have flipped across this way. So this would have went the other way. So it didn't go across the y-axis, only there. So it's reflected in the x-axis, which means you're going to put a negative out here. We'll put it all together at the end. I'm just writing out some clues here. Stretches. Let's look at stretches next. If I was doing a stretch, here's one way to do it. Here's the distance between these two. So this would have flopped over here and went down to here. And it would have looked like this, and this would have flopped down to here. So it would have come down, up, and down. These 2 points would be now these 2 points. Look how far apart these were. Now the scale here is 2. So this was negative 2, and this was positive 1. So initially, that had a distance of 3. Let's look at where they are now. Negative 7 over to there. If I said, well, how far is that now? Well, now the width of that gap that used to be 3 is now 15, which means I've made this graph 5 times wider than it used to be. Therefore, it has a horizontal stretch factor of 5. Now, you got to be careful of that. If the stretch factor is 5, that means the b here must be 1/5. Vertical stretch. Look at how wide the graph used to be. So the top of it was at 4, the bottom of it was at 4. We flipped it over, we stretched it apart, But if I look at the distance between here and here, it did not get any wider this way. So there is no vertical stretch. So the a is going to stay as a 1. But we are going to need a negative 1 out there to flip it, to make it come across the x-axis. So we got that one looked after. We have that looked after. Now we got to look at the left-right movement. Use this point right here. It's probably the easiest one. It's not the only one you can look at, but if that flips over, it should have been there. Even when you stretched it horizontally, this one wouldn't have moved because it was the ordered pair 0, -4. So when you stretch or change your y values, if the x's or the x's, when you horizontally stretch it, this wouldn't have changed. It would have stayed 0. It didn't. It moved. So it must have shifted to the right. How far? 3 units. So this graph has moved to the right 3 units. Now you may say, well, is there any other way I could have done that? Well, you could have. You could have flipped this over. It would have been right here. The y value would have been 2. Right, follow me. Y value would have been 2. Well, then, when you stretched it horizontally by a factor of 5, you would have multiplied the x, not the y. The x would have been 2, so it would have been 2 comma -4. But this point, then you would have multiplied it by 5, which would have put it over at 10. But it's not at 10, it's at 13. So that would be another way to say, oh, okay, I see it moved plus 3. You just got to kind of pick a point and follow it and see where it ended up. So if I write out my function, this would be my function. I don't want to go too far because the answer is there. So the new function g of x was created by doing this. Multiplying f, f was the original, by a -1. That reflected it. -1 times f. I multiplied the x's by 5. That means I need to put a 1/5 here in front of the x. But I also moved them right 3. That's a -3. Now the points did not move up or down because it's still at the same height on the y scale, so there was no vertical translation. There would be a function to get that from there to there. If you doubt it yourself, write a mapping. So let's write a mapping. Say, well, I think this is the mapping. I think I'm going to multiply every x by 5. I'm going to move the x's right 3. I'm going to take every y value and multiply it by a -1. Pick a point on the base graph. So let's pick this one right here, 0, 4. Would you agree that that point is now sitting right there? Hopefully you would. It's now sitting at 3, -4. Well, let's map 0, 4 and see if it ends up at 3, -4. So 0, 4. Some more room here. So I did have the right answer. There's my answer. So 0, 4 would end up at 5 times 0 is 0 plus 3. It should end up at 3. 4, take the negative of it. It should have ended up at 3, -4. It did. So I would be comfortable and feel quite confident I had that right by picking a point and checking it in a mapping to make sure it ended up where it should have. If you thought you got lucky on that one, pick another point. Pick this one, apply it to your mapping, and see if it ended up there. And you could check that way to see if you have the right transformations. So there's a graph and identifying transformations from a graph. That one can be probably the most challenging. This one is a fill-in-the-blank type scenario. So it gives you this. So as soon as I look at this, before I even read filling in this, I don't like the way it's written, so I'm going to rewrite it as g of x. And hopefully if I say, well, what don't you like? I don't like the 4x. I want a 4 and then a bracket. So I'm going to go here, -3 f at 4 bracket x. So it's not going to be 16 anymore. Now it's going to be 4. And then my -10. All right, so let's fill in the blanks here. The function f of x is transformed to make the new function g of x. So the function f of x is transformed to the function g of x by a horizontal stretch about the, well, any horizontal stretch is about the, they mean where you're pulling it away from, it's always about the y-axis. So the answer they were looking for there would be about the y-axis. By a factor of, meaning how much further are you going to make it away from the y-axis? You're going to pull them and make them all go 5 times further away from the y-axis. So your stretch factor for b would be 5. not 5. What am I looking at? I'm thinking of the last question. Don't mind me. It would be a quarter. It's always a reciprocal of that number. So they're going to be 1/4 would be your stretch factor horizontally. C, it is stretched vertically about the, so anytime you stretch it this way or this way, it's from the x-axis. So about the x-axis, that's what they mean by about, from or away from. And the scale factor that you're going to multiply your y values by, a factor of, remember, it's never a negative, it's the positive value or the absolute value of that. Your scale factor is 3, so that one's not the reciprocal. It is reflected, so there's a reflection here. If there was a reflection, if there was a negative here, it would have 2 reflections. This one only has a reflection in, so when you put a negative out front, remember that's switching the y's from positives to negatives or vice versa. So that's when you go across the x-axis. So E would be the x-axis. And then it's translated. So many units to the right. Well, it's 4 units to the right. And how many units down? 10 units down. So there's the blanks all filled in. All right, so this concludes an overview of what are called reflections and stretches. Put that together with translations, and you have now been given explanations of how to apply all the different types of transformations that exist for functions. Translations, reflections, and stretches. So hopefully you can piece that all together. As I said, this section does require maybe some note-taking and some studying like you would do for a history test. There are just some transformational facts that students will be required to know in order to answer the questions. So you can now go on to do some practice questions, and once you're comfortable with the material, there is a formative assessment that will be available to get some feedback on how you're doing. Thanks for watching. Best of luck. As always, reach out if you have any questions or concerns.